Ah, just wanted to start this video out looking at the unit circle. It's a beautiful thing. It's a thing that should be memorized. Even though I'm going to put a copy of this on your Google Classroom page so that you can refer to it anytime. Nice thing about the unit circle is it gives us a lot of common measurements. So going from 30 degrees to pi over 6, 45 to pi over 4, 60 to pi over 3. You guys probably don't know, but I'm not looking at the screen right now. 90 turns into pi over 2. 120 is 2 pi over 3. 135 is 3 pi over 4. 150 is 5 pi over 6. 180 is 2 pi. I'm sorry, 180 is pi. Now you know I really wasn't looking at the screen. 210 is 7 pi over 6. 225 is 5 pi over 4. I know 270 is 3 pi over 2. There's one in between there that I don't remember. Anyways, you get the point. Good to memorize it so that you can do those simple conversions. However, we don't always have a 60-degree angle. What if it's 65 degrees? Or what if it's 95 degrees? See, that's where our challenge starts, because those aren't on the unit circle. So we have to have a way to convert back and forth between degrees and radians. Wow, look at that. Converting between degrees and radians. So to convert radians to degrees, I simply take my radian and multiply by 180 over pi. Convert degrees to radians, I multiply by pi over 180. So that's just the two simple formulas we use to flip back and forth between radians and degrees. Okay, let's convert from radians to degrees. So we'll start by converting the following radian measurements to degrees. Whenever we do this, remember, if we're going 2 degrees, then we do pi over 5 times 180 over pi. Now you'll see what that does there. My pi's cancel out. I'm left with 180 over 5, which is going to give me 36 degrees. Yeah, I'm smart, I know. Part B, do the same thing. So 4 pi over 9 times 180 over pi. Pi's cancel out. 180 divided by 9 gives me 20. 4 times 20 is 80 degrees. 6 pi. 6 pi times 180 over pi. Pi's cancel out. 6 times 180 gives me a lot. I think it's going to be 1080. I'm so smart. So that's 1080 or 1080 degrees. Those were easy. Is it just as easy to convert from degrees to radians? Now there's one simple step that usually occurs in these ones. My writing is ugly today. 75 times pi over 180. So that gives me 75 pi over 180. Do not turn pi into 3.14. It's not the same thing anymore. Don't think about that whenever we're doing angles with radian measurements. Don't use this as 3.14. Leave it as pi. All we have to do now is reduce this fraction. If you have a graphing calculator, you just do 75 divided by 180, math, enter, and it comes up with 5 over 12. Then you throw your pi back in. 5 pi over 12. And that's our final answer. 220 times pi over, my gosh, times pi over 180. Just put 220 over 180 in the calculator. I don't want a decimal either. Give me a fraction form, reduced fraction. I'm sure there's some website that'll do it for you. It gives me 11 over 9. And then put the pi back in like it's still raw. Get it? It's like putting a pie back in the oven. Whatever. All right, next one. 400 times pi over 180. You end up reducing 400 over 180. And you get 20 over 9. Put the pi back in. 20 pi over 9. Done. So pretty easy to convert back and forth between radians and degrees. It's pretty simple measurements. That takes us to arc length and angular speed. The formula for arc length can also be written in terms of radians. So we've already done this with degrees. Now we can do it in terms of radians. An arc with a central angle measure theta radians has length L, or the arc length, is equal to the radius times theta. Wow, that's crazy. I feel like the other formula was much longer. If we go back and look, we had pi r theta over 180. This was our formula for arc length with degrees. Now, it's a much simpler formula because we're using radians. We don't have to do a conversion inside of this formula. So, a second hand on a clock is 6 inches long. How far does the tip of the second hand move in 15 seconds? So, I guess we have to think about how far 15 seconds is. If we're thinking about a circle, here we have a circle. 15 seconds would be going from here to here. That looks like 90 degrees to me, but we're not doing degrees, we're doing radians so that we can do our arc length with a much simpler calculation, which means that this is pi over 2. So it's traveled pi over 2 degrees. Pi over 2 radians, not degrees. You guys are killing me. I miss you guys, honestly. Now I'm just sitting in a room talking to a computer, pretending like it's a class in front of me, knowing that you guys were going to make fun of me that I messed up. It is what it is. Pi over 2 radians. So our arc length is the radius, which is 6 inches long, times pi over 2. That gives us 3 pi. And now that we're dealing with arc length and not the angle measurement, I can put my 3.14 in, or just use the pi button on the calculator. Because we're looking for how long it actually is. 3 pi doesn't tell me anything. This gives me the distance that my arc traveled was approximately 9.42 inches. So this distance of this arc length is 9.42 inches. Find the central angle measurement in radians of an arc length of 5 centimeters on a circle with a radius of 3 centimeters. This comes right back to my formula. L equals r theta. So now I know that my arc length is 5 and my radius length is 3. And that just leaves me trying to find my central angle. Divide by 3, divide by 3. Theta equals 5 divided by 3. And you'd really just leave that as 5 over 3 or 1.66 radians. Remember to make sure you write that radians in so I know that you're using the correct measurement. If you wrote degrees in, that would be wrong. Okay, that's the end of the last part of these notes. I will be giving you some questions on this, and let's see how you do. Remember, if you have any questions, jump on to the Google Meet with me and get your questions answered.